This is oral exam 2. Here's the statement. Here's my signature. Exercise 13, part A. Ask, what is the obvious theorem to use for this exercise and why? I said the fundamental theorem of calculus, and that is because the vector function is conservative. Part B, what would happen to the answer if you reverse the direction of the curve? On your final answer, you'd have to put a negative sign in the front. So if it was negative, it'd become positive. If it was positive, it'd become negative because you're reversing the direction. And then lastly, part C, would Green's theorem work here? And I said Green's theorem would not work here because it is not a closed curve. Exercise 17, part A, asked, why would Green's theorem make sense here? And I said, because C is a closed curve and the integral is in the form of p dx plus q dy. Part B, is the vector field conservative? Like I said, it's in the form of p dx plus q dy, so p is equal to x squared, q is equal to negative xy squared. dq dx and dp dy do not equal each other, so it is not conservative. And then part C is, could you also use the divergence theorem here? And I said no, because it is not a surface integral. Exercise 27, part A, ask, what formula would you use for this and why? I said I would use the formula, the double integral over d of f of x comma y comma g of x comma y times the square root of 1 plus g of x squared plus g of y squared dA. You could use this because you could set the parameterization of r of xy to be equal to x comma y comma x squared plus y squared. X squared plus y squared is g of x comma y, which is equal to z. And then part B, would the divergence theorem work here? And I said no, because we were integrating over a scalar function and not a vector function. And then could we use Stokes' theorem here? I also said no, because we're integrating over a scalar function, not a vector function. Part 4, exercise 29, which of the main theorems would be applicable here? I said we could use the definition by setting the parameterization to be the sphere. This would work, but it'd be very messy. We could also use the equation of the double integral equals negative p gx minus q gy plus r dA. This would also work, but you would have to do two integrals, one for the upper hemisphere and one for the lower hemisphere. This is because r of x comma y is equal to x comma y comma square root of 4 minus x squared minus y squared, but you'd have to do the positive square root and the negative square root, so you'd have to do each hemisphere separately. Best thing to use here would be the divergence theorem. You'd have to use spherical coordinates though. And then exercise 34, the last one, why doesn't Stokes' theorem work here? I said Stokes' theorem requires a simple piecewise smooth boundary curve, which the surface of the cylinder does not have. That's all.